So, all right, so you guys have been asking to stop doing integrals for a while, so no integrals today.
Is this harder?
No. I think it's easier. There's one piece of algebra that's ugly, but other than that, it's easy. It's not hospital, though. All right, so this is indeterminate forms and Hopital's rule. Hopital. He's the mathematician that came up with it. All right, so way back, probably the first quarter of the year last year, we probably came across these indeterminate forms. So if we hit something that's 0 over 0 or infinity over infinity, we can't take its limit. So, yeah. No, it's not. I promise. All right, so Hopital came up with this rule. He determined, so you're going to probably want to write that much down, Hopital's rule, and then write this piece of it down. Okay? So basically what all of that stuff is saying is as long as we have two functions, f and g, and they're differentiable, okay, if we end up with one of the indeterminate forms, the 0 over 0 or the infinity over infinity, another way to get the limit and end up with the exact same limit is to take the derivative of the top function, the derivative of the bottom function, and then take the limit of that, and it will get you the same limit. Okay? In the past, if we've hit one of these indeterminate forms, the only thing we've been able to do is do the chart where you put in numbers that get closer and closer and closer to whatever it is you're finding the limit of. Okay? All right, so we're doing limits combined with derivatives. So the only instruction we're going to have today is evaluate the limit using Hopital's rule if necessary. All the ones that we're going to do, it is necessary. I am going to tell you, because the book tells you examples, what the indeterminate form is. We'll kind of talk about it as we're doing each one. But the book's not going to tell you that in the problems, what the indeterminate form is. Okay? But I wanted to make sure we covered them all. So I kind of wrote it up there for you. Okay, so let's pretend it's the AP test, and you get something like that. Our first inclination is to use direct substitution, right? So if I were to use direct substitution, I get e to the 0. What's anything to the 0 power? 1 minus 1 over 0. So I get that indeterminate form. That's an indicator that I can take the limit of that. I just need to use the Hopital's rule. Okay? So I'm going to do the limit. All right, so all I've got to do Hopital is I got to do the derivative of the top. So I'm actually going to write, when I do, because I'm not always going to do it right at the beginning, so I am going to do Hopital right there. Okay? So what is the derivative of e to the 2x? 2e to the 2x. What's the derivative of x? 1. Now I'm going to use direct substitution again. So I'm going to put in the 0. So what's 2 times 0? 0. E to the 0 is? 1 times 2 is? So the limit's 2. Now, if you really wanted to see it done the long way, they do one in the book that takes like a page of their typing to get the limit of that thing. So this is much easier. Okay? I know the kids that did this independent study, this was the only thing they learned on their own that they got. So, yes. All right, here's example 2. So my indeterminate form this time is we end up with the infinity over the infinity. Well, it was this. Yeah, there's tot. Not that I didn't help them, but they did most of it on their own. Not necessarily, but you do need to have a denominator. Okay, and that's going to be important here in a couple examples. All right, so if I was going to use direct substitution, okay, and I'm putting in infinity, so I'd really have the natural log of infinity over infinity. That's going to go to infinity over infinity, okay? And on some of these, you kind of have to visualize the graph a little bit because there's, natural log of infinity. That's going to be huge, okay? Indeterminate is either the 0 over 0 or if you get one of these, okay, the 0 over 0 or the infinity over infinity, and that's your indicator that you need to use the Hopital.
What did we do before?
You had to use the chart. Okay, we'd have to go in and look at, and we'd have to sub in values. Okay. All right, so I'm going to do the Hopital's rule right there. So the limit as x approaches infinity, so I need to do the derivative of the top, which is 1 over x, which is the derivative of the bottom. So really I have the limit as x approaches infinity of 1 over x. So I'm going to use my direct substitution now. 1 divided by infinity is 1 divided by a very large number. 0. There you go. Okay, here comes the third one. 7.
Oh, okay.
Well, these are the last. There's only 2 more that only take part of a page. So.
Negative infinity?
Yes, that's negative infinity this time.
Children. Like, oh, okay.
All right. So again, we try to do direct substitution. We end up with infinity squared over negative infinity, whatever, and that's just it's gonna end up being infinity over infinity. So that's the indicator that I need L'Hopital's rule. So I'm gonna go ahead and do L'Hopital right here. All right. You can.
Why do you write it?
Because you're gonna see why here in a minute. Okay. Every time I do it, I'm going to write it. Only so that it's an indicator to myself that's what I did in that step. You don't have to write it, okay? But you're going to see that we're not going to do it right away in some of these problems. So I'm doing L'Hopital's rule. What's the derivative of the top? 2x over the bottom, okay? Good. All right. Now let's go ahead and try to do direct substitution on that. So I'd have 2 times infinity over negative e to the negative. So what happens here?
Wait, isn't it negative? Oh no.
Doesn't really matter, does it? I get infinity over infinity again, don't I? So I have in another indeterminate form. So every time I get an indeterminate form, Hopital again.
Oh.
So you might have to do this more than one time. All right, so what is the derivative of 2x? 2. Okay. What's the derivative of negative e to the negative x? E to the negative x. All right, now let's go ahead and use our direct substitution. So I've got 2 over e to the negative infinity, which is really just 2 over infinity, which is 0.
Is it determined on the x-factor or the exponent?
What?
How many times you're going to do the L'Hopital? If it's like a square, then you can do it twice. Is it like to infinity?
I haven't probably done enough of them recently to tell you that for sure, but probably. What's wrong, Jonathan? You're going to need this on the AP test. Guaranteed. Okay. You could have used this last year on the AB test.
Are they going to tell us on the test when you
No. You have to recognize the indeterminate form. So, speaking of indeterminate forms, oh, I forgot to finish this slide. Nice. All right, so these are not recall. These are other indeterminate forms. So another indeterminate form that might pop up is 1 to the infinity, infinity to the 0, 0 to the 0, and infinity minus infinity. That one doesn't come up, actually.
That was perfect. Oh my God.
So.
That's pretty awesome.
All right, so what we're going to do is we're going to do one more example like each one of those. Okay, so you've seen at least one. There is some funky algebra that goes on in a few of these. Okay, I'm not changing it yet. But again, if you hit one of those forms, you know you have to use the Hopital. Okay?
You guys are gonna get sick of that because I'm just like saying it. What? I'm just kidding. Don't say it.
What's a little ho-to-ho?
All right, here's the next one. Same instructions. Shh. Pants are falling apart.
Is that 0 to infinity?
Why?
They're like the little fuzzies are already coming out. I only bought them yesterday.
You bought them yesterday?
Ellie picked them out for me. Can you tell? Target didn't have a very big selection. Walmart did? Oh, okay. I wasn't going to go that far. Plus, I had to get Monsters University yesterday, and I know Target always has the copy that I like. So, okay. So, in this case, we're going to end up with this form here. So let's think about it for a minute. We've got e to the negative infinity square root of infinity. So that, if we were to look at the picture of e is like this, right? So if I'm going to go towards, notice it's saying the limit towards negative infinity, the closer and closer I get to infinity, I go to 0. So that's why this one comes out 0 times infinity. Okay, that's an example of one where you need the picture. Okay, so, but as long as you kind of know what the exponential looks like, that's not too bad. All right, so I'm going to go ahead and use the Hopital. Before I do, though, I remember in order to use the Hopital, I need to rewrite that.
Oh.
To have a denominator, this doesn't work. That's part of the theorem. Okay. I would probably even go so far as writing it as x to the half e to the x. So now I'm going to go and use good old Hopital. So do you see why I'm not using it until the second step? Okay. So what's the derivative of the top?
1/2 x to the negative 1/2.
Good. And the derivative of the bottom? E to the x. All right. I'm going to clean it up before I try to sub anything in. So the limit as x approaches negative infinity of the 1's going to stay upstairs. The 2 square root of x e to the x is downstairs. Now I'm going to sub in. So 1 over 2 square root of infinity. Just going to end up being infinity, isn't it? No matter what I do to the bottom, it's going to end up as infinity. So I'd really have 1 over infinity, which is 0. All right, you ready for the fun part?
This is the fun part.
Yeah, this is going to be the fun part.
Oh, that's 0 from the right.
From the right. So the limit as x approaches 0 from the right of sine x to the x. This time our indeterminate form is okay, so if I tried to use direct substitution, sine of 0 is what? 0, and then to the 0 power, so the indeterminate form popped up. I know I need the Hopital, okay? On this one, and this is the same pattern whenever we have an x to an exponent of x, okay? We're going to use this method.
X to an exponent of x?
Yes, yeah, okay? We've got the only way to get that variable out of the exponent is to use logs, okay? So, and this is one where we get some weird fancy algebra. I don't want to know. Okay, so.
You should show us a picture. It's hilarious. You're going to die laughing. You'll love it.
All right.
You're a math teacher. You'll love it.
All right, so all I did right there was add y equals, okay? Now, in order to get that variable out of the exponent, I'm going to take the natural log of both sides. So natural log of y, and technically, we can eventually shortcut this here, but technically, we have to put the natural log on the outside of the limit. Yeah, well,
I've never seen it. Yeah, I've never like a limit.
I know, it looks weird. And then there's some property, I think it was, I didn't write it down. Let me see. Oh, wait, maybe it's on this page.
After this problem, can I show
Because the function is continuous, all right, we can have you seen like one of the latest Big Bang Theories where Sheldon's in his zone?
No.
Oh yeah, it was pretty funny.
Literally in a zone.
Yeah, and he doesn't want to be interrupted. Okay, so because it's continuous, I'm allowed to move that natural log in. We could have probably done that all in one step. Okay, I might on the next problem. All right, so technically I'm allowed to move that natural log in of sine x to the x. Okay, because the function's continuous. All right, now what would I normally do with that x with the natural log? Throw it to the front by our log properties, right? So natural log of y equals the limit as x approaches 0 from the right of x natural log of sine of x to the x. All right, here's the problem.
Why to the x?
Oh, I'm sorry. I didn't mean to put my x there. I was just writing. I wasn't. Here's the problem. I can't use the Hopital unless I have a fraction. I don't have a fraction. Okay, what? No. Okay, so, because I want it in one variable. All right, because it says the limit is x approaches 0. So, I'm not going to mess with my trig. Here's where the funky algebra comes in. Okay, and it took me 2 sittings to figure this out. This is why they pay me. Okay, because you just get to hear it. So, what I'm going to do is technically there's a 1 in the denominator, right? I'm going to multiply top and bottom by 1 over x. Okay? So here's why I used 1 over x. Because 1 over x divided by 1 over x is 1, right? So I didn't change my function in any way. But it allows me to get rid of this product rule and get rid of that x in the numerator.
So do you have to deal with the natural log of the x on the y later?
Yes, this comes at the very end because this cancels, right? 1 over x times x is 1.
Isn't it 1 over x squared?
No. I should have written it like this.
Oh, okay.
Okay, so it cancels. All right, so really what I have there, let me write it a little bit cleaner, okay? So the natural log of y part comes in the very end. All right, so we kind of have to keep it going there. So I have the natural log of sine of x over 1 over x is what I'm trying to find the limit of. All right, so let's see what happens if I use direct substitution on that. Okay, so I have, what's the sine of 0?
0?
What's the natural log of 0?
1.
It's supposed to go to negative infinity. Oh, I know what I did. I graphed it. So if you graph the natural log of sine of x, it ends up being something like this. So as I go towards 0 from the right, it's going to negative infinity. Okay? All right, then this here, when I put it in, when I do 1 divided by 0, what do I get? It's technically, it goes to, if I were to graph it, oh, I know why, it's a graph again. If I were to graph it, I would get the negative infinity, because it's a hyperbola. Probably like that.
So it's 1?
So no, negative infinity over negative infinity is one of our indeterminate forms.
Oh.
Okay? So if I have an indeterminate form, what do I have to do? L'Hopital's rule. So I hadn't even done L'Hopital yet, right?
What's the difference between infinity over infinity and infinity over negative?
Huh? There isn't. Okay? What's wrong?
What you put up there, how you indeterminate form when x is 0 to the 0, that wasn't.
That was, all we've done so far is manipulate algebra. We haven't done L'Hopital because we didn't have a denominator yet. Okay? So we got another indeterminate form, same deal. Because the first thing you want to do when you see something like that is if you can rearrange it, rearrange it. Okay, and sometimes it'll pop out. You know, sometimes we'll get something to cancel. We can factor and cancel something. Well, we rearranged it and got another indeterminate form, which means we have to use L'Hopital. We haven't done it yet. We couldn't do it before because we didn't have a denominator. All right, so let me erase some of this stuff so we can keep going. Told you this was the fun part. All right. It's not that, once you get to here, it's not that terrible. Okay, so now I'm going to do L'Hopital. I'm going to go ahead and put it up here at the top. So here's when I'm going to actually take my L'Hopital right here. So I'm keeping the natural log of y the way it is. I'm only dealing with the derivative on the other side. Okay, so what's the derivative of the natural log of sine x? 1 over sine x times cosine x. Notice how I wrote it. I did it that way on purpose. Okay? All right. This is technically x to the negative 1 power, so it's the derivative of that. I like the negative.
What do you have?
I have x to the negative 1 power, so what's the derivative of that?
Negative 1 over 2x.
Over x squared, right? Because it's x to the negative x to the negative 2. We subtract 1. I know it's been a while since we've done derivatives. Okay? And then you want to put that denominator back down. Okay, so if I have cosine divided by sine in the numerator, what do I really have? Cotangent. Cotangent of x over 1 over x squared. Okay, so let's see what happens if I sub in there. Okay, so cotangent of 0 would be cosine divided by sine, which is 1 over 0, which gives me something that's like undefined, doesn't it? Which is, we could kind of consider 0, I guess. All right, and then we have 1 divided by 0 again, which means we are, so don't we have another indeterminate form there? Yeah, so we got to keep going. Let's do another L'Hopital. Okay. Before I do it, actually, I'm going to rearrange it just a little bit, make it simpler. Okay. So what's another name for cotangent? In terms of tangent. 1 over tangent. Okay, so I'm going to put my I'm going to take the cotangent downstairs by making it tangent. And then can't I flip and multiply this?
Yes.
Yep, so that's going to bring it upstairs. That's a little bit simpler. Now let's do L'Hopital on that. So I'm going to do L'Hopital again here. So the natural log of y equals the limit as x approaches 0 from the right. What's the derivative of the top? Over what's the derivative of the bottom? Okay, now let's try subbing in. So we get 0 in the top. What's secant of 0? 1 over cosine, which is 1 over 1, which is, what's 1 squared? 1. So I have the natural log of y equals what? 0. Okay, I've got it. Now I've got to solve for this y. So we are going to exponentiate it. So we get y equals what? 1. All right, way back at the beginning, I would probably go back up here, and either I'd write it down here at the end, the limit of whatever equals, or in this case, we know that that's going to equal 1. That one wasn't pretty. I'm not moving it. The hardest part, though, it's that piece of algebra that's right there in the red. If you don't know how to get to that piece of algebra, it makes it difficult. It was just, we did L'Hopital twice in that one. But do you see why I keep writing it? Because where we do it is in weird spots. So that at least is just a mental note. Okay, that's what I did there. Okay? All right, you ready for me to keep going? All right, next one.
What's your picture? Oh, since it was an exponent.
Oh my gosh. That's funny.
You have to read it ghetto though, like ghetto.
I need to see this.
Read the top comment. You have to read it in the ghetto voice though.
Why don't you
So
take Why did you take that X from me?
Okay.
Hilarious. What is he, Jonathan?
No, I'm sorry.
Jonathan?
right. So, if we were to put in, infinity? 1 divided by infinity is 0. So I end up with 1 to the infinity. So I hit one of the indeterminate forms, which means we have to use the Hopital somewhere, right?
Wait, since it's like a fraction on one side or not. Never mind.
Okay, so we just learned this in the last example. Whenever I have that x to an x,
Oh, natural log.
I'm going to have to use natural logs, and then I have to introduce the y. So y equals the limit as x approaches infinity of 1 plus 1 over x to the x. All right, let's see if we can shortcut this one a little bit and not do quite as many steps as we did in the last one. So what am I supposed to do to both sides? Natural log. And we took the natural log on the outside, but we learned that we can just put it on the inside, right? So natural log of y equals the limit as x approaches infinity of the natural log 1 plus 1 over x to the x. Some of you might even see that we could just throw that x out in front, right? Okay, and that's okay. So now we're at the point where we've got the limit as x approaches. Stop.